Okay, we've been given an example to do at the end of our motion facts. The example has a position function s of t equals t cubed minus 6t squared. So that's right here. And they told us t is going to be greater than or equal to 0. And they asked us simply when is the particle speeding up and when is it slowing down. So we've done this before. We need to basically find the velocity and the acceleration and want to find out when those two functions have the same sign. So I'm going to go ahead and slide this up, and we'll start with velocity. How about in some blue? So the velocity, remember, is always just the derivative of the position function. So that would be 3t squared minus 12t. And then let's see, for the acceleration, that would be the derivative of velocity, which will be 6t minus 12. All right, so now for velocity, we'd like to find out when that is equal to 0. And we'll just draw a little separator line right here. And that's equal to 0 when 3t times t minus 4 is equal to 0, doing a little bit of factoring. And that means when t is equal to 0 and t is equal to 4. So v equals 0 when that is happening. And then we'll do the same kind of thing over here for acceleration. We want to set that equal to 0. And that occurs when, well, I don't think we need to do factoring here. We could just say 6t equals 12 and t equals 2. So a equals 0 when t is equal to 2. Okay, so now it's time to bring these two together on a sign chart, a Waco graph. So we'll start with how about a number line like so. And we'll put another one down low like this. And the first one we're going to call v of t. Second one is a of t. And underneath that is t. So here we go. Let's go ahead and put some markers on here. So we'll have 0 for our time. And we want to get over to 4, of course, because that's our other critical value for the velocity. And we're going to test the signs of the velocity, and we'll probably use our nice little factored form here because that one's really convenient to plug in values. So we'll plug in something over here, we'll plug in something here, we'll plug in something over here. Actually, no, we're not going to plug in anything over to the left of 0. We'll plug in something here in the middle between 0 and 4, and then above 4. Okay, so let's go plug in, how about, I don't know, t equals 2. So let's do that. If you plug in t equals 2, we're going to get a positive here, we're going to get a negative here, and a positive times a negative is a negative. So I like to just put a whole bunch of negative signs right here. And we know that the velocity is 0 when t is equal to 4, and also when it's equal to 0. All right, let's go above the 4. So now if you plug in something like 5, you'll get a positive here, and you'll get a positive there. So that'll be a positive all the way out. All right, moving on to acceleration. So this time, let's see, we've got 0 here. We want to keep these lined up. 2 would be somewhere about here in the middle. And let's see. Now, 0 is not really a critical point there. It's just we're not going to go below 0. Okay, because they told us in the beginning that t had to be greater than or equal to 0. So let's go plug in some values of t. How about left of 2, which would be like 1. 1 goes in, you're going to get 6 minus 12, which is negative. So we're going to get negative signs over here. And of course, the acceleration is 0 here. Now, if we go to the right of 2, so we're plugging in something bigger than 2, like a 3, we're looking at like 18 minus 12, and that's going to be positive. So that'll be all positive out there. All right. And I didn't keep with the color coordination here. Those should have been reds over there, but I guess we get the idea. So let's highlight some things. So right here we have the same sign. And then over here we have the same sign. And we know when we have the same sign, we're talking about speeding up. Now we have opposite signs in between here, so that means we're going to be slowing down at those times. All right, so then we'll just write a little statement down at the bottom. Here we go. Therefore, 3 dots, the object is speeding up on 0 to 2 and 4 to infinity. Because velocity and acceleration are the same signs there. We can also say, and I'm realizing right now, I probably should have had that be a capital T. The object is slowing down on, let's see, 2 to 4. Oops. Let me clean that up a little bit. It looks a little funky. So 2 to 4, because, let's see, because V and A are opposite signs. All right, there we go. Okay, continuing here. We've got an example 2, and they ask for the total distance from t equals 0 to t equals 6 for a particle, and the position function is t cubed minus 12t. Okay, and at first glance, you might be thinking, well, total distance, I can just integrate. But sometimes we'd like to look at it differently. And this is one of those times. So we will come back to the integration idea later. I would like to break this down a little differently. So let's just draw a little line here to separate. We're going to go find the velocity. And we're going to figure out when the velocity changes signs. So the velocity is just simply the first derivative, of course. We'll set that equal to 0. We're going to factor. We can factor out a 3. That'll leave a t squared minus 4. And then, of course, you could factor that into t plus 2 and t minus 2. And that means we have 2 times where the velocity was equal to 0. And, of course, we'll ignore the negative 2 because we're talking about moving forward, and time starts at 0. So there's one time at t equals 2 where the particle is changing directions. So, I mean, visually, maybe we could look at it like this. Here's a little wiggle graph for v of t. You can add this to your paper. There was a negative 2 over here, and there was a 2 over here. And we can plug in values right and left of the 2. So let's go bigger than 2, like a 3. Let's put something in over here. And if you plug in a 3, this will be positive. That'll be positive, positive. So that's all positive. So that means moving to the right. Here it's 0. In between negative 2 and 2, our favorite number would be 0. In fact, I'm going to plug in here. That'll be even easier. 0 goes in, you get 0 minus 12. You get a negative in here. And then left of negative 2, like negative 3 or 4 or 10. So negative 10 would be, let's see, negative here. That would be a positive over there. Okay, so we're really going to start at time t equals 0, though. So if you picture time t equals 0, it's going to be moving left, first of all, and then it's going to be moving right. So left and then right. All right. So what we like to do is figure out the position at those specific times. In fact, I think I'm going to get rid of this line right here because I'm going to need that space. So I'm going to make myself a little timeline here, like so. And when I say timeline, I'm really talking about position. I'd like to know what the position is. So starting off, the position we're going to say is equal to 0 right here, kind of in the middle here. And if we plugged in 0, if you look back at the function, s of 0 is equal to 0. You can plug in here and you can plug in there. You're going to see it's equal to 0. Next up, we're going to plug in s of 2. And we can find out that that's 8 minus 24, so that's negative 16. And then lastly, I'm going to plug in the 6. Now I'll come back to these values and talk about why we're using these. But that's going to be 6 cubed, which is 216, minus 12 times 6, which is 72. And that's going to get us, I think it's 144. Yeah. Okay, so let me talk about why we chose these values right here, 0, 2, and 6. So 0 is the beginning of time. It says right here to use t equals 0. We're going to stop at t equals 6, and that's the end of this discussion. Well, at t equals 2, that's the special case where basically we're saying that the particle, the object, whatever this is, it's turning around. It was moving left, and now it's moving right. So here's what we're going to do. We're going to keep track of all the things that this particle was doing. We're going to start with position 0, and we're going to put a little point right here, and we're going to say t was equal to 0, and it was at position 0. And then it was still moving left. If you look over here, you can see that the velocity was negative. So it was on its way left, and it went a decent ways, and then it went over here. And this point where it turned around, that's when the time was 2. So we'll say t equals 2. And the position over there is negative 16. Next up, it continued to the right really forever. So I'm just going to go ahead and throw an arrow over there. It's going to the right forever. Because over here you'll see on our wiggle graph the velocity never changes. It's going to stay positive from t equals 2 on out to the right forever. But what we want to do, and this is not drawn to scale, let me put a t, no, not a t equals, sorry. This is an s equals negative 16 down here. What we have over here on the far right, if we were to pick a spot and talk about that t is equal to 6 right there, we can mark the position. That would be s equals 144. All right, so now we have all the values we need. So we're going to keep track from the beginning. We'll start right here. This is leg 1, and we'll change colors. Let me make that a little bit thicker. So how about right here? That's good. And then here is leg 2. Now that leg 2 can actually be broken up if you'd like. We can call it leg 2 and then leg 3 if you'd like. So what I'm saying here is this first leg, the orange leg, that would be, let's see, let me go ahead and write out total distance. We traveled 16 units to the left, and then we traveled 16 units back. That's right here in the orange. Oh, excuse me, the pink. And then after that 16, we traveled this distance right here, which is 144 from the 0 spot. So we're going to add 144. Now if you put that all together, you will get 176 units. So that's one little technique. That's kind of nice. You get a little visual display. I like it. It gives a nice little visual display of what's going on. We investigate what's going on with the velocity and how the velocity changes signs. And we pretty quickly get to the total distance. Now, there are other ways, so let me go ahead and draw a little line here to separate. We could have also done this, total distance, so add this to your paper. We could have taken those 3 times, t equals 0, t equals 2, and t equals 6. So those 3 times. And we could have said, what's the difference in position? So I'm going to go s of 2 minus s of 0. And I'm doing this in absolute value. That way it gives me a distance and it won't give me negatives. So s of 2 minus s of 0. Plus, I'm going to do it again. I'm going to go the absolute value of s of 6 minus s of 2. Now, in doing this, we're going to find the 2 legs, and that would be, let me see if I can highlight this a little differently. Maybe I'll circle them in some green. So s of 2 minus s of 0 is going to give me this section. And then separately, we're going to see, let me switch to some blue here. We're going to go s of 6 minus s of 2, which will be this section. And that's going to take us all the way down from the 6 down to the 2. Okay, so let's go ahead and calculate, and you'll see how this works. Because it works out actually pretty slickly. All right, s of 2, we already know, was negative 16. Looking at our notes a little bit earlier up. S of 0 was 0. So if you look at that calculation, that's already going to get you a 16. Which makes sense, because this green section right here was 16 units. Now, the weird one. We've got to go from 144 down to the negative region, down to negative 16. Oops. Let's see how that works out. So, s of 6, we know was 144, minus s of 2, which was negative 16. And we all know when you subtract a negative, you are adding a positive, so that'll be 160. And the absolute value doesn't do anything in this case because it's already a positive, and there it is, 176 units. All right, same answer, of course. Now, what we did here, these guys right here, if you would reverse those and reverse those, it does not matter what order that you subtract these in because you have an absolute value. You're finding the absolute difference. All right, and just to finish it off, let's go ahead and do it the slickest way, which would be, I think you know, total distance. We've done it recently. It's going to be the integral of the absolute value of the velocity. So we're going to take our 3t squared minus 12 in the absolute value symbols, and we're going to do that from 0 to 6. All right, and if you just punch that in the calculator, you will get 176, just like before. Of course, this is the slickest way, but it is possible that they give you a question that basically pushes you to do it in this way that we've done up here, where you're either going to be subtracting inside some absolute value, or maybe just looking at a diagram. Maybe it's a function that you don't really know how to find the derivative easily to get to the velocity. That's not super likely, but it is possible. It could be that they have something set up like this already. Oops, didn't mean to erase all that. It could be they have something set up like this right here, and they ask you what it represents. And they're not going to tell you the total distance part. They're just going to ask you, what does this stuff on the right mean? And you should recognize that the change in position, but it's the absolute change in position, and the same thing over here. And when you add them together, you're getting total distance. All right. Okay, so to generalize, here's what we need. We needed the beginning point, the ending point, and all turnaround points. Okay, so as a sample, let's throw one down here. So let's just say sample, so you know this, we don't have specific numbers here. And let's go with, how about some blue again? So let's say we go with s of 0. and then we have S of 3, for example, and then we have S of 4 and S of 6, and let's say S of 13 is the last one, and let's say this S of 0, that's the beginning, and this over here is the ending, and all of these guys here in the middle, ooh, that's pretty. These are the turnaround points. We'll just call them turnarounds. That's where the v, the velocity, was equal to 0. All right. So, with those in mind, we can take all that information right there, and we can say that the total distance is equal to, now I'm just going to start with a couple of them here. I've got my first two. I could go S of 0 minus S of 3. I really don't care what order you subtract them. Plus, next up I'm going to go 3 to 4. S of 3 minus S of 4. Plus, next, you guessed it, S of 4 minus S of 6. Plus, our last pair, S of 6 minus S of 13. All right. We don't have all the values for those, but imagine having all of those. You would work those out. And again, the order here does not matter. You can switch these. It will not make any difference. Okay? It's kind of like this. If you were to take something like the absolute value of 7 minus 5, is that the same as 5 minus 7? And the answer is, of course, because you get 2 on this side, and you get negative 2 on this side, but they're both in absolute value. So we're both talking about a distance of 2 between the values of 7 and 5 or 5 and 7. All right, there you go.